Hello, welcome. In this short video, let us look at the operational definition of the impulse function or the impulse signal as applicable to the linear time invariant systems. First, let us look at the motivation behind this new definition. It is motivation. Recall that in a previous video we have discussed that an impulse signal can be approximated by a rectangular pulse. That is, recall delta of t can be approximated by a rectangular pulse and it becomes the impulse signal in the limit. This limit delta tends to 0, delta of t, where delta of t is basically a rectangular pulse defined as follows. The signal is equal to 1 by delta when the value of t is between 0 and delta and it is 0 elsewhere. So this is the definition given previously for an impulse signal, or at least its relation to the rectangular pulse. But this limit based definition is not very useful for LTI systems. This definition is better for analysis of the value of the signal at particular value of time, but it is not so useful for LTI systems. So let us look at the operational definition of the impulse signal for LTI systems. So the operational definition is based on convolution operation. So we are going to use the following definition, that is x of t is a signal. It is equal to the convolution of x of t with the impulse signal. So that is the operational definition of the impulse signal. So x of t is equal to convolution of x of t with the impulse signal. It is analogous to unity in multiplication. So what are the implications of this definition? So implications. The first one is we arrive at one of the properties of the impulse signal. That is, the area under this impulse signal is actually equal to 1. So how do we know this one? We can actually derive it from the operational definition. So let us write the definition again. X of t is equal to integral minus infinity to plus infinity delta of tau x of t minus tau d tau. So that is the definition of convolution operation. Now if we assume that x of t is actually equal to 1 for all values of t, that is, if you assume that x of t is just unity for all values of time t, then we have 1 is equal to integral minus infinity to plus infinity delta of tau d tau, because this value is also equal to 1 irrespective of the shifting. So we have this property, that is, the area under the impulse signal is equal to 1. Now let us look at the second implication. The second one is basically any signal at time t equal to 0 can be defined as integral minus infinity to plus infinity g of tau delta of tau d tau. So that is the definition of the initial value of a signal based on the impulse signal. So to verify this one, just replace x of t with g of minus t in the operational definition. So we'll get, that is, when we replace x of t with g of minus t, we have g of minus t equal to convolution between g of minus t and delta of t. So it will be g of minus t equal to integral minus infinity to plus infinity delta of tau, and then we have x of t minus tau, but x of t minus tau is replaced by g of minus t, so it will become g of tau minus t. So the variable is reversed, and then we have d tau. Now just put t is equal to 0, that is, compute the initial value. So we have g of 0 is equal to integral minus infinity to plus infinity delta of tau g of tau d tau. So that proves this second implication. So if you look at the operational definition again, it is basically the shifting property of the impulse signal, or it is actually, so we use this one as the operational definition of the impulse signal for LTI systems. So to summarize, in this video we have looked at the operational definition of impulse signal as it pertains to the LTI systems. So motivation for this definition is as follows. Recall that we assumed, or we introduced the impulse signal like a limit for the rectangular pulse, or we can use the rectangular pulse as an approximation to the impulse signal, and as the width of the pulse becomes smaller and smaller, it gets closer to the true value. So but this kind of definition is not so useful for LTI systems. So to overcome this problem, we have an operational definition for the impulse signal, which is given by the definition x of t is equal to x of t convolution with the impulse signal. So this is the operational definition. So because of this, there are two implications. The first one is the area under the impulse signal is equal to 1, and the second one is for any signal g of t, the value g of 0 is given by the integral minus infinity to plus infinity g of tau delta of tau d tau. So that is the second one. Therefore, in the analysis of LTI systems, we use this operational definition for the impulse signals. Thanks for watching.